All right, thanks everybody for coming. We're excited to have you all here today. Um, for those of you who haven't been to one of the quantum speaker series, we hope to have time at the end. So please put your questions in the Q&A and we'll get to them as we can. I am Allison Schwartz, the industry co-chair of the Quantum Working Group here at ATARC, and we're excited to have Dr. Kate Weber come and talk to us about Google's quantum and AI mission. Kate leads the global public policy for AI and emerging technologies at Google, including AI and quantum, and her career focused on the intersection of scientific research and policy. Prior to Google, she led the team at the US Department of State, covering bilateral agreements, multilateral engagements on chemical management, air quality, and waste management, where she was also an American Associate for Advancement of Science and Technology Policy and a Policy Fellow. She holds a PhD of molecular biology from the University of Cambridge, where she was a Marshall Scholar, and a BS in biochemistry and molecular biology from the University of Richmond. And with that, Kate, I will turn it over to you. We're excited to hear from you.
Thanks so much, Allison, and nice to see everybody. I am going to present on Google's quantum computing work today. Please tell me if you can't see the presentation. I think it's all set up, but I'm not always.
Yep, we can see it. We're good.
On Zoom. So, okay, great. And I'll just jump in. I think there should be hopefully plenty of time for a discussion at the end as well. So, yeah, Google's approach to building a useful quantum computer. Topic for discussion today. I'll talk about our overall mission and the progress on that mission so far. So, as everybody probably knows at its core, Google is a computing company, but we all on this call, I assume, also know that we can solve many problems with classical computers, but not all of them. And this is why Google is investing in quantum computing, to be able to access those classes of problems that we don't think we can solve without a quantum computer. So I've skipped the slides that are kind of introduction to quantum computing, given the audience here, and I will jump in and just talk about Google's specific effort. We are working on superconducting qubits. As everybody here probably knows, research teams are working on many different types of qubits. They all have their kind of strengths and weaknesses. Our team is focused on superconducting qubits, which are made with using aluminum on silicon chips and using Josephson junctions, which you can see a picture of here on this slide, to encode the quantum information. This kind of pendulum graphic that you see on the right hand of the slide is depicting the different states of the qubit. So you can think of the kind of zero state of the qubit as the lowest energy state, its ground state. We excite these qubits using microwave photons and excite them into this one state where the pendulum is swinging in its excited state, and it's the frequency of 6 gigahertz. And you can see kind of what this looks like on one of our chips here, just to give a sense of what it means when we say we are using superconducting qubits with Josephson junctions. So we all know that building a useful quantum computer is a major challenge. This is Google's roadmap to building a quantum computer, and our goal is to build a computer with 1,000 long-lived logical qubits that's error corrected. We think of this as the kind of full scale endpoint that we're working towards in this R&D phase that we are in now. Google's quantum computing team, Google Quantum AI, I should say, is part of Google Research. It's very much viewed as one of our next big bets, but also as a kind of early stage pre-commercial effort at Google. We don't currently have a commercial offering for our quantum computing service. And so you can see there are 6 steps along this roadmap leading to that error-corrected quantum computer. We are at milestone 2 right now. We just achieved that this year. I'll dive in a bit more to what these first 2 milestones are on this timeline. But just to say, going forward, the next milestone that we're working towards is this long-lived logical qubit. We hope to achieve that by 2025 plus, so 2025 is likely the earliest. Once we have that, we believe we can kind of tile it together into gates and then begin the engineering scale up to get to 1,000 of these logical qubits. But if you look at the orange numbers on this timeline here, you can see that we currently are on the order of 100 physical qubits. In the end, we believe we will need to get to about 1 million physical qubits. So as you can imagine, going to be a lot of engineering challenges along the way just to fit all of those qubits and their supporting electronics and cryogenics and everything into the space that we have for the quantum computers. So quantum bits, qubits, are fundamentally error prone, and this is one of our central challenges in building a quantum computer. And so this slide depicts different types of errors that you can have in quantum bits, and you also see on the left-hand side of this slide these spheres, which are a typical way that we show the fate or the kind of state of a qubit. So there are different kinds of errors. You can have flip errors where the qubit interacts with its environment in a way that kind of knocks it into the wrong state. These can come from all kinds of environmental factors, solar rays, like other kinds of disturbances. You can have measurement errors. So the process of measuring the states of these qubits itself is imperfect, and we might set it in one state, but register it in a different state because there was some error on the measurement side. Control errors. So there's a lot of hardware between the control signal that says, okay, we want to put this qubit in a one state, and the actual qubit. And this kind of clip art on the right here is designed to show that it's really like a long game of telephone, and there can be errors at any point in that control process. And so practical quantum computing is going to require some kind of error correction. Each qubit is ideally supposed to hold its quantum state, but in reality, they're error prone. We have to both improve the quality of the qubits, but also be able to correct for these errors when they do happen. At Google, we are relying on something called quantum error correction to reach this useful fault-tolerant quantum computer stage. And what that means is that we are pooling together a large number of faulty qubits to correct for each other and together hold one quantum state better than the single qubit could on its own because of all those errors. And our team is particularly interested in what's known as a surface code, which relies on a 2D array of qubits, which is shown here in this little blue and yellow square, where half of the qubits actually store the data, or the qubit states, and the other half are used to measure and trace errors. So on this little blue and yellow square, each of these kind of circles with the lines, the spokes coming off of it is a physical qubit taken together. It's meant to indicate a logical qubit. And I believe the yellow qubits on here are the ones storing the data, and then the blue qubits around it are the ones that are measuring and correcting for errors. So this relies on some assumptions, this sort of theory of error correction. It assumes that all the errors in the quantum system can be captured by measuring these bit and phase flip errors on individual qubits, and also that we need to control the noise within the entire system pretty well. So what we'll talk about today is the experiment to test a prototype of a quantum error corrected logical qubit prototype. basically. And yeah, I mean, I think that there's this graphic on the top kind of shows the sequence of steps of the error correcting qubits checking the measurement qubits for error. So the yellow squares are depicting the states of the qubits, zeros and ones. You can see the kind of red, blue, and purple lines are measuring errors and then correcting for errors, and then in the end, decoding and identifying like, okay, on this green qubit, there was an error, we're gonna fix that, basically. Just to kind of go back one step and talk about how we got to the current milestone. So the first step in establishing this error-corrected logical qubit prototype is to build this surface code compatible chip and show that a quantum processor can outperform a classical computer at something. And this is, we call the beyond classical computing milestone. Google achieved this result in 2019, where we used what we like to call kind of a toy problem, a problem that doesn't have a real world application, but showed that in theory, our quantum processor could complete a calculation that it would have taken at the time an estimated 10,000 years to complete on the Summit supercomputer at Oak Ridge National Lab. It is important to note that comparison with a classical supercomputer was with the classical supercomputer available at the time. So our quantum chip from the time compared to today's classical supercomputer, the delta there would be different, but we've also been, both of these systems are developing and improving in parallel, and we will have updates to share on our end in the coming months on this beyond classical comparison with today's supercomputer. And the graph that you see here is just showing the kind of this cross entropy benchmarking refers to the calculation that was done on the quantum chip, and the delta at these various fidelities for that benchmarking between the classical supercomputer and the quantum chip. So we call this milestone the beginning of the NISQ era, the noisy intermediate scale quantum processor era. So the next step after this milestone was to test these quantum error correction principles that I outlined in the previous slide and verify that at least at small scales, this thing that we think will work in theory does in fact work in practice. And so this is the second milestone that we announced a few months ago. Before I dive into the details of that, I did want to just give you a sense of the progress that the team has made between 2019 and 2023 that's allowed us to achieve the second milestone in the roadmap. So the system has greatly increased in the number of gates. The gate error has gone down both for single qubit and 2 qubit gate error, even though we're using a different type of gate now, where reducing that error is actually more challenging than it was for the FSIM gates that we were using before. We've reduced readout error, so the error in kind of reading the state of the qubit from the chip, the time it takes to do that readout, like figuring out what state the qubit is in. And we're also now, we didn't have a measurement before, but this reset error refers to when you kind of reset the system and do the next phase of the calculation. So these milestone 2, M2, reducing errors by increasing the number of qubits and using quantum error correction. So this we announced in February of this year, it's published in Nature. I kind of went through this in principle, so now we'll talk about what this looked like when we tested it on our chip. So again, the principle here is you encode information, you use those extra qubits around the measurement qubits to check repeatedly for errors and then decode and kind of go through cycles of calculations in this way. On this graph, the larger code, so using more qubits is shown in blue, and the smaller one is in red. We used 17 qubits for the smaller code, 749 for the larger code in this case. And what you see on the graph here is the number of quantum error correction cycles, so the number of times you're going through this process, and the logical error probability on the y-axis. So of course, as the more cycles you have, the more the probability of having an error, because you have just more chances to have an error. What we want to see is that the probability increases more for the smaller code than for the larger code, because in the larger code, those correction qubits are correcting errors and able to keep that error down over time in relative terms. So effectively, we want the red line to be above the blue line, which you can see it is here, but you can also see it's barely, there's like not much of a delta, right? So we've essentially barely crossed this threshold where error correction can be used to keep the errors down for a larger code relative to a smaller one. Of course, this still means introducing a lot of errors over time. This is shown in kind of a different way on this graph, where you look at the number of qubits on the y-axis, the number of errors, sorry, number of qubits on the x-axis, errors on the y-axis. Ideally, the error should go down a lot as you increase qubits, because you're increasing the number of qubits you have available to do this error correction. So for milestone 2, for the work that we announced earlier this year, that slope is like barely a slope, right? You're barely decreasing the errors as you increase the number of qubits. Lambda refers to the ratio of decrease in errors versus qubits. So we call this a lambda of about 1. We think that in order to get to our next milestone, which is a long-lived logical qubit, in more precise terms, this long-lived logical qubit is a logical qubit that could perform 1 million calculations on average before introducing any errors. So in order to get to that point, we think we need to get to a lambda of 4. So that's a big improvement in the error correction capabilities. And that's the team's major focus over the next few years. And we have these kind of incremental points along the way, lambda 2 and lambda 3. So that's kind of where we are and where we're going over the next couple of years on our hardware roadmap. I want to talk a bit to the applications side too, and I know there are probably lots of folks on here with additional expertise across all of these spaces, but on our side, you know, this is a chart kind of showing how we think about the potential quantum computing applications for various numbers of physical qubits. Again, just for the sake of consistency, these numbers here refer to physical qubits, just as those I showed on the hardware roadmap did, though these physical qubits all correspond to smaller numbers of logical error corrected qubits in practice. We at Google have a team working on that hardware development. We also have a team working on quantum algorithms and applications, including many of those listed on this slide. So some of the earliest stage applications that we see and predict are in areas like fundamental physics, quantum gravity, many body states, certified random numbers. As you get to slightly higher numbers of physical qubits, we start to think about spectroscopy applications. So many of these applications are related to molecular modeling. So things like fundamental physics, spectroscopy, novel phases of matter. But then there are other areas to quantum machine learning with quantum data. What that means is we see predicted advantages to machine learning on a quantum computer when the quantum computer is ingesting, or this isn't something we've done experimentally, but we predicted if it's able to take data from, say, a quantum sensor, so quantum data, and use that in machine learning, there will be a huge advantage versus a classical computer, which I think is also sort of logical. Larger scale molecular modeling for, manufacturing, drug targets, et cetera. Particular kind of data analysis, topological data analysis. We see potential advantages for machine learning using classical data as we get to larger numbers of qubits, and then even more advanced molecular modeling applications getting in the range of 5 to 50 million physical qubits. And this is also in this range where we believe quantum computers will be able to achieve factoring, so to break RSA encryption. So just to talk in a bit more detail about some of our recent advances in applications, I've got a list of papers here. I'm by no means an expert on all of these topics, so I'm not going to go into a lot of detail on them, but wanted to put this slide up to give you a sense of the kinds of publications our team has been putting out on the applications side. And these align with some of the broad categories that I had laid out on the previous slide. So the first, formation of robust bound states of interacting photons. This is kind of a fundamental physics experiment. Quantum advantage in learning from experiments. This is quantum machine learning. Non-abelian exchange statistics, fundamental physics. Again, same for transversal wormhole dynamics. This last one, resource estimation to assess electronic structure of cytochrome P450. This is a paper looking at a potential application for fault-tolerant quantum computers in molecular modeling. So just to give a sense of the team's work here. And then, of course, we're also thinking a lot about the broader context in which we're operating in, and I could, talk a lot more about this since this is kind of my area of focus on the public policy team, but just to touch on a few themes of sort of how what we are doing fits into the broader ecosystem and the need for collaboration and, government support, et cetera. So we are part of this broader industry. We don't know, as I mentioned, we consider this effort to be we think it's very promising, but it's a research effort. It's not clear yet that the superconducting qubit architecture is the one that is going to win out in the end. And we're very interested in following developments in other qubit architectures as well, and think that the collaboration across the community is super important. This slide lists a few of the kind of our efforts in the workforce space in particular, which is a big challenge for us, and I know for many of our peer companies as well. Just recruiting talent, we expect this to become an even bigger challenge in the years to come as we move on the hardware roadmap from the early stage, where much of our staff is physicists, to bringing on more engineers, more technicians. It's going to require not just more of the kind of workforce we have now, which is challenging enough, but also different kinds of employees, engineers, technicians, people to maintain our facilities, more people on the business side. So some of Google's efforts in this space are, we're developing some new training videos on YouTube. We're funding research, including PhD fellowships and faculty awards, but also undergraduate research. We have some workforce development efforts kind of targeting some of these new or non-PhD physics types of roles, training people to work in chip fabrication facilities, et cetera, with some of the institutions listed on the slide. And we recently announced a large partnership on the margins of the G7 with the universities of Chicago and Tokyo, which cuts across many of these education and workforce development themes as well, funding at various levels, workforce development for technicians, funding for startups in the quantum space. and happy to kind of dive into any of these topics further too, if that's of interest.
Kate, we do have some questions that have come in, so I'd love to see if we
Yeah,
can.
I'm looking at my slides rather than at the Q&A.
No, I'd love to be able to have you talk in. So there was a couple questions that came in about why does the quantum machine learning with quantum data need fewer qubits than the quantum machine learning with classical data?
Yeah, so this is and thank you for the question, Charles. And I will preface this by saying that I am not a quantum computing technical expert, so I will do my best, but I'm also happy to follow up and to connect you with the researchers if you would like more information. And I think, Allison, I'm happy to share my email at the end too. But I mean, the basic sort of conceptual idea is that if you think about the qubit as obeying the laws of quantum physics, and the quantum sensor, like say you're getting data, you know, from a sensor, like measuring levels of some molecule in a person's blood, and that's reading out the data to some kind of like through some system. Like the quantum sensor is also obeying the laws of quantum mechanics, so you don't have to translate the data into a classical binary format and then translate it back into the quantum format if you're communicating directly between say a sensor and a quantum computer. So that is the kind of conceptual idea, but I'm sure that our scientists could explain it much more thoroughly at a technical level if you're interested, so please feel free to follow up.
We also had a question, and you mentioned it on the slide of, you know, Google has, you know, looked at superconducting qubits, but, you know, you're also very interested in other ones. There's a question here that just came in, you know, is Google all in on superconducting quantum computers?
Yeah.
And can you talk about why Google chose that approach?
Yeah, happy to. Yeah, so the answer is yes, we are all in on superconducting quantum computers, at least at the moment. And we've chosen that approach for a number of reasons. A big one is that we believe this using quantum error correction is a viable near-term path to creating the fault-tolerant quantum computer using superconducting qubits. They're also they have relatively fast readout and measurement speeds compared to some other architectures that tend to be very slow, and I think so far in our view haven't proven that they can move at the speeds that would be necessary to do, you know, 1 million calculations in a feasible amount of time. There's also just a lot of the kind of like infrastructure for building the systems is a bit more established, and yeah, so that's the summary, though I think definitely acknowledge that things are early enough that it's very possible other architectures could pull ahead. We're not saying that this is the only place Google is going to operate in the long term, and on the span of decades. And it's also, I think, very possible that one qubit architecture may be the first to achieve what we call fault tolerance, but not be the predominant one in multiple decades from now.
Thanks so much, Kate. On the timeline on your roadmaps, you had mentioned the milestone 2, which was a few years since 2019. I know it's hard to predict, but do you know when milestone 3 might be? This is a question asked. I
think it may actually have been like this. So we're targeting 2025. I think what the slide said was 2025 plus. So we like to be ambitious in these numbers, and the sort of overall scale of the roadmap we've said in the past is about 10 years. So, the goal is I would say, ambitious goal is to try to do this by the beginning of the next decade. But yeah.
Perfect. There are a lot more questions, but we only have 1 more minute. So I am going to I'm going to just ask one quick question, which is on the immigration side and the talent side. Kind of what is your hope for getting the talent in, and the role that the State Department plays in that?
Yeah, so as I mentioned, talent is a huge priority and focus for us. It's a huge challenge, even for a large company like Google, to get all the talent that we need. I think anything that can be done to speed up the visa application adjudication process to allow people to renew visas while staying in the US, to kind of expedite visas for priority areas like quantum computing would be very welcome. And we're very focused on this dual-pronged approach of bringing in the talent that from outside the United States, while also developing the talent kind of nationally, and also in our case locally, in Santa Barbara, where our facilities are located.
Well, we are 1 minute past time. Thank you, Kate, for such an amazing presentation. We will share the recording of this on the ATARC YouTube channel, as well as Kate's email. She has graciously said that she would be happy to connect with folks offline to be able to answer the questions we weren't able to get to. Thank you all for being here, and have a great day.
Thanks, Allison. Thanks, everyone.